So much for the introduction and for the opportunity to give this talk here today. It's great to be able to connect with everyone across this distance. So I will be talking about global existence results for 2D Kuramoto-Sivashinsky equation. And what I'll be talking about is joint work with Anna Mazzucato from Penn State. Okay. The Kuramoto-Sivashinsky equation is a fourth order parabolic evolution equation, and it might model a few different things. It primarily is a model of flame fronts. It's primarily an equation that comes from combustion, but there are other contexts in which it arises, such as some notion of thin films. Like if you, I think I've read that if you are having a thin film flow down an inclined plane, you get the Kuramoto-Sivashinsky equation or something very much like it. Okay, but I'm interested in it as a model of flame fronts, as a model coming from combustion, where I believe it, at least by Sivashinsky, it was originally derived that way. And so it's this fourth order parabolic evolution equation, dt phi plus 1/2 grad phi squared equals minus bi-Laplacian of phi minus Laplacian of phi. And one thing you might like to have for such an equation is a maximum principle. And it being fourth order, there is no maximum principle. So if you look at the sign of the two linear terms, the bi-Laplacian has a good sign. The bi-Laplacian is the dominant term because it's fourth order, and it is stabilizing. So this is a well-posed forward parabolic equation, but the Laplacian, the lower order linear term, is just the Laplacian there. That Laplacian is destabilizing. It has the wrong sign. So you get some backward growth from the Laplacian, but you get good forward parabolic decay from the bi-Laplacian. So these two linear terms are in competition with each other. In general, the bi-Laplacian wins, but that competition leads to the very rich dynamics that Kuramoto-Sivashinsky displays. Because it is a forward parabolic equation, because of the bi-Laplacian, short time existence results are easy. You can prove a short time result in any dimension for relatively rough data without too much effort, because you do have this dominant leading order forward parabolic term. Existence for all time, though, is much harder. So we'll be talking about existence results for all time, where you really have to contend with the backward parabolic term. And this global existence theory is well understood in 1D, but what we'll really be addressing in this talk is the fact that there are very few results in 2D. There are all sorts of other results other than global existence, especially in 1D. Those include existence and stability of traveling waves. There are a lot of other results, especially in 1D. We won't be going into that. There are also a number of results on modified equations. So, for example, if you were to eliminate the bi-Laplacian and change the sign on the Laplacian, you arrive more or less at something that people have called the Burgers-Sivashinsky equation. And that's well understood. For the Burgers-Sivashinsky equation, you do have a maximum principle, and you can get global existence in whatever dimension based on the maximum principle there, at least for small data. But we'll be talking about the full Kuramoto-Sivashinsky equation, and we'll be talking about global existence results for the 2D case. Okay, so I mentioned, I talked at some length already about the linear part. but this is really important. So I want to go into some detail with this now. So the linear term in the equation is minus Laplacian squared minus Laplacian. To understand this, we want to have a good, clear picture in mind of how this acts. So let's be explicit about the symbol of this linear operator in the 1D case. So let's say we're considering the periodic 1D case with spatial period L. So you could write a Fourier series, phi of xt is just the sum over all k and z of ak of t e to the 2 pi I xk over L. So we can take was there a question? Maybe not. Okay.
No. Okay.
Okay. So we can take 4 space derivatives of that, and we can take 2 space derivatives of that. And every time we take a space derivative, we get a 2 pi k over L. So the symbol of the linear part is minus 2 pi k over L to the 4th plus 2 pi k over L squared. So this does what you expect for a parabolic equation. For sufficiently large k, this symbol is always negative, right? We have k to the 4th plus k squared. So that regardless of whatever L is, you have 2 pi over L along with each k. Regardless of what L is, for large enough k, this is going to be negative. It might be negative for all non-zero k, depending on L. And it's not hard to check. The condition for that is that if L is less than 2 pi, so if your period cell is very small, then the symbol is actually always negative. So you get no growth from the Laplacian on small boxes, on small period cells. So for large values of L, larger than 2 pi, there will then be a finite number of modes for which the symbol is positive. So the dynamics depend on this. The dynamics depend on how many linearly growing modes are. You can imagine if you have no linearly growing modes, then the solutions are all just going to decay to 0. You can imagine if you have, say, 1 or 2 linearly growing modes, you might get some non-trivial dynamics. And if you have, say, 1 million linearly growing modes, you might get some very complicated things happening, where eventually everything decays, but there's a lot of stuff going on where you might get basically the Kuramoto-Sivashinsky equation is known for chaotic dynamics. And you can see that if you have a large number of linearly growing modes, you can see how the dynamics would become chaotic. Okay, so this is a description of the linear part in 1D, but the same thing holds in 2D. For large enough values of k, where k would now be 2-dimensional, this would be negative. On small period cells, on small period cells, you have no linearly growing modes. And in between, you have, for general L, you might have some finite number of modes for which the symbol is positive. Okay. Now, in 1D, you have another good feature. So I'll talk about the global results in 1D. In 1D, Tadmor proved that the solutions always exist for all time. So if you take the Kuramoto-Sivashinsky equation and differentiate it, you let u be dx phi, then the equation for the differentiated version of 1D ks is this: dtu plus u dxu equals minus dx fourth u minus dx squared u. So you have the same linear part, but now the nonlinear term is the Berger's nonlinearity, u dxu. And of course, that has a great structure. If I multiply by u and integrate, u squared dxu integrates out to 0. So that means that this differentiated version has a good L2 estimate. Now, it's not exactly that the L2 norm is conserved, because you might have linearly growing Fourier modes. So on the dx squared u, when you multiply by u, you're going to, and integrate by parts, you don't get decay from the dx squared u, you get growth from the dx squared u. It's okay because you get decay from the dx fourth u. Okay, but you can't say that the L2 norm is conserved. You can just say that you get a global L2 estimate for this differentiated version of 1 dks. So Tadmor leverages this L2 estimate into a global existence result, including higher regularity. You know, you do get parabolic gain of regularity. So this L2 estimate is really the crux of Tadmor's global existence result in 1D. And I believe it's accurate to say that Tadmor allows the solutions to grow exponentially based on the exponential growth you get just from the linear part for a general size of the domain. Okay, this nice structure of the nonlinearity is not present in 2D. I won't make any calculation for that, but your differentiated version in 2D, you have two components. You have u and v, where u is dx phi and v is dy phi. And if you differentiate u squared plus y squared, you get u dx u, and you get another term that does not have the good conservation structure. Your nonlinearity is not conservative the way it is in 1D. So anything like Tadmor's argument is not possible in 2D. Okay, another very important paper on 1D Kuramoto-Sivashinsky is by Jonathan Goodman in 1994. And so I said that Tadmor proved that all solutions exist for all time, allowing exponential growth. Goodman shows that the growth does not always occur. So he shows that small solutions don't exhibit the exponential growth. And the solutions aren't really small. It's not saying that the solutions have to be size epsilon for some small enough epsilon, but the solutions have to be small enough. In particular, in Goodman's result, there exist functions C1 and C2 such that if the initial data is of size C1 of L, so again, L is the size of the period cell, then the solution remains of size at most C2 of L. And these are both like L to the 5/2. Okay, so if the initial data is like L to the 5/2, then the solution remains of size L to the 5/2. Okay, and so Goodman's proof uses a Lyapunov function. He shows that a function of the solution decreases in time when the size of the solution is sufficiently large, so that functional bounds the norm of the solution. And I'll go through Goodman's argument in more detail. But therefore, the solution can't get too large. And the Goodman version is what Mazzucato and I use in our 2D result. But there is prior related work. Goodman's result didn't appear in a vacuum, and there is prior work of Nikolenko, Shorter, and Teimam. Okay, so Goodman does this for arbitrary sizes of the domain, for every possible domain size, but he has a really nice exposition, including a description of how his Lyapunov function works on a domain with just one linearly growing mode. So he says if the domain size L is between 2 pi and 4 pi, then the first Fourier mode is the only linearly growing Fourier mode. So he gives a toy model where he considers just two modes, the A1 and A2 Fourier modes, and he cuts off the evolution of those, ignoring any contribution from the other modes. So he makes a toy model with just two modes, A1 and A2, which we'll call X and Y. And if you write down the evolution equations for those first two modes and how they influence each other and ignore all the other contributions, then you get this simple model. X dot equals X minus XY, and Y dot equals minus Y plus X squared. Okay, so this captures the linear behavior. The first mode, x, is growing linearly. The linear part there is x dot equals x. So that's your linear growth. And the second mode, y, is linearly decaying. So you get y dot equals minus y at the linear level. And then the nonlinear terms, the x nonlinear term is x dot equals minus xy, and the y nonlinear term is y dot equals x squared. Those are the interactions between the first and second Fourier mode that you get from the Berger's nonlinearity, that you get from ut equals ux. So this has the right nonlinear behavior for just the first two modes, and it has the right linear behavior for just the first two modes. And Goodman shows that what the nonlinear term does is it allows energy to transfer from the one mode to the two mode. So the one mode wants to grow linearly. It starts growing, it builds up some energy, it transfers that to the two mode. The two mode then lets that input of energy decay because the two mode is decaying. And so this gives a global bound, okay? And we see the global bound through a Lyapunov function. Okay, and Goodman says in this that it's important that the nonlinearity here is conserving energy. So he says that it's important that you have the L2 estimate from the nonlinearity. Okay, and so we're going to generalize that in our 2D work. We're going to see that you don't need exact conservation to make this work. Okay, so the Lyapunov function for the toy model, again, Goodman gives a great exposition of this. He really shows the idea behind the general argument by giving a very clear picture on this toy model. So Goodman gives this Lyapunov function, f of xy equals 1/2 x squared plus y squared minus 2y. Okay, and then he does what you usually do with the Lyapunov function. So he shows that if f is large enough, then f dot is negative. So if f is greater than or equal to 8, then f dot, meaning df dt, is less than or equal to 0. He shows that if x squared plus y squared is less than or equal to 4, then f is less than or equal to 8. He shows that if f is less than or equal to 8, then x squared plus y squared is less than or equal to 48. And so then you can combine all these things. If x squared plus y squared initially is less than 4, then f initially is less than 8. If f is less than 8, then f cannot surpass 8 because f dot is less than or equal to 0 for f bigger than 8. And so then f at all t is less than 8. And so then x squared plus y squared for all t is less than or equal to 48. So that's the global bound for the toy model. If the initial data squared is bounded by 4, then the solution squared at all times is bounded by 48. Okay, and that's going to be a key ingredient in our 2D result. Okay, for a long time, there was only one 2D result, and that was by Sell and Tabuloda. And that was in 1992, and that's a thin domain result. So George Sell was known for being one of the leaders of thin domain theory, I think, for Navier-Stokes. And so Sell and Tabuloda extended those thin domain ideas to Kuramoto-Sivashinsky. So the 2D periodic domain in the thin domain result is taken to be of the size 0L cross 0 epsilon. And the epsilon is quite small. And so you know that 1D solutions exist for all time. So by 1992, that was known that 1D solutions exist for all time. And they show that the solutions remain quite close to 1D solutions. So they were adapting thin domain theory by Hale, Rogel, and Sell. So much use is made there of the vertical average. So given a function f, the vertical average is 1 over epsilon integral 0 to epsilon f of x, y, t dy. I'm not an expert on thin domain theory, but basically that vertical average, you've averaged out the 2D direction and the second direction. So that vertical average behaves a lot like the solution of the 1D problem. Okay, and other authors over the years have continued the thin domain approach. There's a work around the year 2000 by Luc Molinet, and then there's more recent work, I believe, by Igor Kukovica and collaborators. And they've expanded the thin domain results, working with this vertical average still, working with the vertical average and talking about how big the epsilon can be. And maybe the epsilon gets big enough so that you still would consider, maybe you don't consider for all of the results the domain to quite be thin anymore, but the results are still strongly anisotropic. The results are still treating one dimension as fundamentally different from the other. So in the work Anna Mazzucato and I have done, we want to get beyond these anisotropic results and really treat the two dimensions as being similar to each other and allowing square-like domains instead of requiring one of the sizes to be small based on the other. Okay, so what we're driving at is we're going to try to get away from anisotropy, get away from thin domain type results. Even if the domains aren't always very thin, we don't want to use this vertical average. We want to really treat the problem as the two directions as being equivalent to each other. Okay, and so a couple years ago, I think maybe we submitted it around 2017 following some time at ICERM. There was a special program on fluids at ICERM, and Anna and I were both there, and we were able to work together. And we finished our first 2D result on Kuramoto-Sivashinsky at that ICERM program. And there's several results in the paper, and I'm only going to describe one of the results that Anna and I did in this first paper. But it's based on a technique I learned in my PhD student's thesis. My first PhD student, Timur Milgram, finished in 2011, and he studied, he generalized some work of Duchon and Robert from the 80s on vortex sheets. So Duchon and Robert, in a paper I like a lot from 1988, proved existence for all time of some unregularized vortex sheets. And so that's an ill-posed problem, but they found certain solutions which exist for all time. And they used an analytical technique based on the Wiener algebra. And so then I've used this Wiener algebra technique since my student Timur learned the technique and taught it to me. And so I've been using this for several years since then. So the Duchon-Robert problem is for elliptic problems. The unregularized vortex sheet is ill-posed, and it's ill-posed because it's elliptic in space-time. But it turns out, other than elliptic problems, the framework also applies to parabolic problems. So I've used this for both kinds of problems since then. Milgram, Bona, and I applied this to show ill-posedness of certain ill-posed Boussinesq equations. So what are called the Bona-Chanceau generalizations of Boussinesq equations. But I've also applied it for parabolic problems such as mean field games and for a problem in epitaxial growth, epitaxial thin film growth. So Anna Mazzucato and I used this Duchon-Robert method on 2D Kuramoto-Sivashinsky in our first paper on this together in 2017. And that is, this first result without anisotropy is in the absence of a linearly growing mode. So remember we said that for small enough periodic cells, you have no linearly growing modes. And so that's the simplest case then of 2D Kuramoto-Sivashinsky. And we don't have any anisotropy there. The domain could be a square as long as both dimensions are less than 2 pi. Okay. It doesn't have to exactly be a square, and it could even be thin. All we need is that both dimensions are less than 2 pi. Okay, so I'm going to describe this Kuramoto-Sivashinsky framework. So it lets us get solutions for all time primarily by just using function spaces on space-time. Whatever your spatial domain X is, your overall domain is X cross 0 infinity. So the fact that the solutions are global is built into the function space. We consider functions on space-time from the start. So our spatial domain here is going to be, our X is going to be 0, L1 cross 0, L2. So our rectangle, our periodic cell with dimensions L1 and L2. And so that's the spatial part. And then the temporal domain is, from the start, it's the interval 0 to infinity. We use the Duhamel formula for the equations to formulate the solutions of the PDE as a fixed point problem. So the fixed point map, if you do the Duhamel formula, you get U equals the semigroup applied to the data plus the Duhamel integral applied to the nonlinearity. And so that's a fixed point formulation of the PDE. So then you prove boundedness of the linear operators. The linear operators are the semigroup and the Duhamel integral. So you prove boundedness of those linear operators on the function space. These function spaces based on the Wiener algebra. And using the boundedness of those linear operators, you're able to show that the mapping is contracting on a certain ball in the function space. So since you are doing a contraction mapping, you get a unique fixed point, and that unique fixed point is the solution of the initial value problem. These function spaces based on the Wiener algebra, I said that these are space-time versions of the Wiener algebra, so you automatically get existence for all time, and you also have an exponential weight on your Fourier coefficients, and so you also automatically get analyticity for all positive times. So analyticity and global existence are built into the choice of the function space. Okay, so let me just say a word about the Wiener algebra. So the Wiener algebra is the space of functions with Fourier transform in capital L1 or with Fourier series in little l1. So this Wiener algebra has a great, very simple algebra property. You can see just from our convolution property of a product of Fourier transforms that so the norm in the Wiener algebra is the L1 norm of the Fourier series in the periodic case. So the norm of Fg is the L1 norm of the Fourier coefficients of Fg, and you can bound that by the sum over all j and k of the absolute value of f hat of k minus j times g hat of j. And then you just sum first in k and then in j to get that that's bounded by the norm of f times the norm of g. So this is a very nice, very simple algebraic property. Okay. So we actually need this in space-time. So in space-time, we augment this by taking the supremum in time of the Fourier coefficients. So given an alpha greater than 0, I introduce an exponential weight also. Alpha could actually be 0, but we're going to use this with alpha greater than 0. But we introduce the exponential weight, e to the alpha t absolute k. We multiply the Fourier coefficient f hat of tk by that exponential weight. We take the supremum in time, and then we sum in k. So this is a perfectly good Banach space. It has the same algebra property. You can just do some manipulations with supremums, and you see that you get the same algebra property for the same reason. And because of the exponential weight, there you have that the Fourier coefficients decay exponentially in time, and so that means that you have radius of analyticity with radius at least alpha t. Okay, so I will say, I didn't invent this space-time version of the Wiener algebra. I got this from the Duchon-Robert paper, and it's not exactly how they describe it, but it's in essence what they're doing. And there's something a little mysterious about this, because we usually, if we have a space-time function space, we almost universally always do the space norm first and then the time norm. So, if you're doing, L infinity in HK, HK in space, L infinity in time, HK in space, you would take the HK norm in space first, and then you would take the supremum in time. Okay, this is reversed, where the first thing I'm doing is the supremum in time, and then I'm doing the spatial norm. This works very well. So it shouldn't really matter. It doesn't feel like it should matter which one you do first, the spatial norm or the temporal norm, but something about doing the time on the inside of the space norm, something about that works very well. And we're able to get a lot of nice results with this version of a space-time norm. After seeing this kind of norm, Bob Strain was able to use this to a nice effect on a problem as well. There's something very nice about this doing time first and then space. Okay, so back to the fixed point formulation. So again, we're going to be using this space-time version, this analytic and space-time version of the Wiener algebra with a fixed point formulation. So our fixed point formulation, again, is just the Duhamel integral. So if our evolution equation is ut equals a of u plus n of u, where a is the linear part and n is the nonlinear part, we can write the Duhamel formula u at time t equals the semigroup applied to the data plus the integral from 0 to time t of the semigroup suitably arranged times the nonlinearity. So that's the fixed point formula. If the operator on the right-hand side, it's an operator applied to u, we want that to equal u. Okay, so that's our formulation as a fixed point. And if n is superlinear, then we have some hope of this being a contraction. Okay, we also want n to involve at most as many derivatives as a. What's going to happen is you can bound the Duhamel integral. You end up doing an integral of this exponential. When you integrate the exponential, you get a, or actually you get the symbol of a in the denominator. When you integrate e to the sa, you get a in the denominator. And so that's the parabolic gain of regularity. If a acts like 4 derivatives, we get minus 4 derivatives. We gain 4 derivatives in the Duhamel integral. And as long as n has fewer than 4 derivatives, then we have the right mapping property for our fixed point map. So n has to have at most as many derivatives as a. And that's great for us here because our n only has 1 derivative in Kuramoto-Sivashinsky, and the linear part has 4 derivatives. So we're perfectly set up there. And I said to get the contraction, we want n to be superlinear, and it's quadratic in Kuramoto-Sivashinsky, and so that's great. So this is going to work out fine for Kuramoto-Sivashinsky. So we're going to get a contraction for small data. And just a little more detail on that contraction, writing it a little more symbolically, our fixed point formulation is phi equals s phi naught plus I plus n. S is the semigroup. I plus is the Duhamel integral. So I plus is the operator that is the integral from time 0 to time t of the semigroup suitably arranged applied to the nonlinearity n. So S maps a space B0. So B0 is just the Wiener algebra itself to B alpha, where B alpha is the space-time version of the Wiener algebra that I described. For small enough alpha, S maps B0 to B alpha. And we can show I plus is a bounded linear operator for the reasons I was saying, that the nonlinearity only has 1 derivative, whereas you gain 4 derivatives from the semigroup. I plus is a bounded linear operator on B alpha, again, for alpha suitably small. And then the reason, so I go through a little detail here of why we want the nonlinearity to be superlinear. If we had n of v was v squared, then we'd have I plus of n of v1 minus n of v2 when we're doing our contraction estimate. The fact that I plus is bounded means you can bound that by c times n of v1 minus n of v2. Then you substitute in n is v squared, so you get v1 squared minus v2 squared, which you can factor. When you factor it, you can use the algebra property. So it's bounded by c times v1 minus v2 in B alpha times v1 plus v2 in B alpha. And so then if v1 plus v2 in B alpha is small, then this is the contraction estimate. So you need c times the norm of v1 plus v2 in B alpha to be less than 1. And so if v1 plus v2 is small enough, all that means is that we're doing this, we're doing the contraction argument on a certain small ball in B alpha. So on that ball in B alpha, you get the contracting property. And that's basically the existence argument. There are only some small unimportant complications to that. And so that's the first theorem. That's our first isotropic global existence theorem in 2D. So that theorem is that if L1 and L2 are both in the interval 0 to 2 pi, alpha star is something, there's some fixed value of alpha star. If alpha is in 0 to alpha star, if U naught and V naught in the Wiener algebra are small enough, then you have a solution for all time of 2D KS on the domain 0 L1 cross 0 L2. Okay, so it was important that L1 and L2 each be in 0 to 2 pi. The estimate on I plus that I described, where you invert the operator A, where you get the inverse of the operator A in the semi-group estimate, that inverse is only going to have the right properties if the symbol of A is negative for all K. And so that only happens with L1 and L2 each being in the interval 0 to 2 pi. So if you had a growing mode, if L1 or L2 were a little bigger so that you had a linearly growing mode, then you can't do this. Okay, so we want to do that though. We want to let L1 and L2 be such that you have a linearly growing mode. So that was a global existence result without any linearly growing modes. The question then is, how can we extend to allow a linearly growing mode? And even better than one linearly growing mode is one linearly growing mode in each direction, because that would really be new. The anisotropic results that started from Sell and Tabuoda and have gone through the more recent work by Kukovica et al. The more recent, or those anisotropic results do allow linearly growing modes. They even allow arbitrarily many linearly growing modes, but in one direction only. So the domain size has to be so that the growing modes are only in the one direction. Okay, so the other direction is quite small. So we want to do this without any anisotropy, and we want to allow square domains, say, where each side of the square is a little bigger than 2 pi. Okay, and I'll say just a little personal history. I got into this because I was a postdoc at the Cron Institute, and I was put under Jonathan Goodman's supervision. So when I arrived at Cron in 2002 as a postdoc, they said, we've assigned Jonathan Goodman to be your postdoctoral mentor. And he said, this was 2002, he said, you know, I had this paper in 1994 about 1D Kuramoto-Sivashinsky. It would be great if you could do the 2D version of that. And so, you know, I guess it's nice that he had that confidence in me, but it's, to give a postdoc such a notoriously difficult problem as the 2D Kuramoto-Sivashinsky problem, it was frustrating for a while because honestly, it took on the order of 15 years to even get the first theorem on that, the first theorem being the one that I just described with no linearly growing modes. So after 18 years now, in 2020, Anna and I finally got this with one growing mode. After 18 years, we were able to use something from Jonathan's paper to get a better result. But over those years, over these 18 years, I've had one bad idea over and over again. So I'm going to describe this bad idea. If you have one linearly growing mode, what if you write down its evolution equation? You consider all the other modes to be forcing for that one mode, and so you solve for the one linearly growing mode in terms of the others. Then substitute that into the evolution for the remaining modes, and the remaining modes are all linearly decaying. So this is a little like doing a Lyapunov-Schmidt decomposition. You kind of have one bad mode, you're going to consider it separately and solve for everything else. Okay, so that's a bad idea though. It's a bad idea because the growing mode looks like it grows. It might not actually grow, right? Goodman's work showed that you don't actually get the exponential growth that the linear part suggests you might get. But if this is what I'm doing, I'm solving for the one linearly growing mode in terms of the others, then when I solve for it, I'm going to have that exponential growth explicitly, right? If I have A1t equals A1 plus F, where F is some forcing, then the solution of that's going to have e to the t in it. So it looks like that linearly growing mode is growing, even if it is not actually. And that explicit e to the t term is going to really seriously impede any effort to show that small solutions remain small. So finally, after many years, we had a new and better idea, which is to use Jonathan Goodman's toy model. Instead of treating one mode specially, treat two modes specially. So you have the linearly growing mode, but you also have the second mode, which is a place for it to transfer its energy to. So we're going to treat two modes specially instead of one. So we have the linearly growing mode, we have the second mode, those two form a little subsystem, and then we treat everything else as smaller forcing. Okay. So Goodman said in his paper that his model really was relying on conservation of energy. And so we realized that it's actually more robust than that. We can modify Goodman's toy model to allow small forcing. So we take the following generalization of Goodman's toy model. Xt equals epsilon x minus xy plus f1, yt equals minus y plus x squared plus f2. So we've made two modifications to Goodman's toy model. One is that we put in the forcing terms f1 and f2, and the other is that we put in this epsilon. We are allowing the growing mode to grow only slightly, okay? So this corresponds to what we get if the period cell has length 2 pi plus epsilon, and if we don't completely ignore the contributions from the other modes. So Jonathan cut off F1 and F2, he zeroed them out. He said, I'm going to completely ignore the contributions from the other modes. So now, instead, we're replacing that with allowing the contribution from the other modes, as long as those contributions are small. So in the absence of forcing, with the epsilon present, the equilibria of the system are that x is like epsilon to the 1/2 and y is like epsilon. If f1 and f2 scale like epsilon squared, then for small enough epsilon, we can prove that the scalings hold up. So this toy model, if the initial data is like x is like epsilon to the 1/2, y is like epsilon, and if f1 and f2 are like epsilon squared, then we can repeat Goodman's Lyapunov function argument to show that the scalings hold up. So for all t, x stays bounded like epsilon to the 1/2, and y stays bounded like epsilon. And then we're going to use this in 2D Kuramoto-Sivashinsky. We're going to use Jonathan's toy model as the basis of a proof for global existence of small solutions for 2D Kuramoto-Sivashinsky, where we have a linearly growing mode in each direction. The A10 mode is linearly growing. The A01 mode is linearly growing. Their energy is going to transfer to the A20 and A02 modes respectively. And we have the rest of the solution, which we're going to call W. So we decompose a solution phi. Phi is the solution of the 2D Kuramoto-Sivashinsky equation. We write phi as the first mode in the x direction, plus the second mode in the x direction, plus the first mode in the y direction, plus the second mode in the y direction, plus the remainder W. Okay. We do this with an iteration. So if you start at the bottom of this slide, our phi n is our nth iterate of our solution phi. Phi is what I just said. It's the first mode in the x direction, plus the second mode in the x direction, plus the first mode in the y direction, plus the second mode in the y direction, plus everything else. And then we have iterated equation for each of these 5 components, right? So the A10 equation, you have epsilon 1, A10, so you're growing a little bit. Then you have the correct interaction between the 10 and 20 modes. And then you have some forcing, which comes from all the other modes. The A20 mode, you have decay, whatever the decay rate is based on L1. Plus you have the correct quadratic interaction between the A10 and A20 modes, plus you have forcing from all the other modes. And then the same thing in the 0-1 direction, or for the 0-1 mode, the same thing for the 0-2 mode. And then you have just everything else for W. The P5 in the W equation is the projection away from those first 4 modes. So we have 4 modes we're treating specially. W is the projection onto all the remaining modes. And so you have that corresponding projection in the W equation. So this is our iterative scheme. And so we get uniform bounds with respect to n. The iteration parameter is n. We get uniform bounds with respect to n by induction. So we assume the initial data scales correctly. Scaling correctly means that the linearly growing modes A10 and A10 and A01 scale like epsilon to the 1/2. The next special modes, which are going to be where they sink their energy into, A20 and A02 scale like epsilon, and the remainder W scales like epsilon to the 3/2. And that norm of W is in one of these Wiener type spaces, one of these space-time versions of the Wiener algebra. So we initialize the iterative scheme with the data, and then we want to show the corresponding bounds for the iterates. Given the bounds on the previous iterate, we established the forcing functions do scale like epsilon squared. That's because the forcing functions, the worst kind of term in the forcing function, the forcing terms are from the nonlinearity. The nonlinearity is quadratic. So if you look at quadratic interactions between the different pieces of the solution we have here, you say, could we have a 1-0 mode interacting with itself? Well, that's not in the forcing function. That's explicitly split off. So the 1-0 mode interacting with itself is not part of the forcing. Could you have a 1-0 mode? Could you have a 1 mode interacting with the 2 mode? That looks like it would be size epsilon to the 3/2. Well, the 1 modes interacting with the 2 modes are not in the forcing. Those are explicitly accounted for in the iteration. So everything else is going to be smaller than that. If you have a 1 mode interacting with W, then that's of size epsilon squared. If you have a 2 mode interacting with W, that's of size epsilon to the 5/2, which is even smaller than epsilon squared. If you have a 2 mode interacting with a 2 mode, that's of size epsilon squared. So the forcing is going to be of size epsilon squared. We're able to establish that bound. Given that bound that the forcing is of size epsilon squared, we're able to use our version of Goodman's Lyapunov function argument. We're able to use our generalization of his argument to show the bounds on the next iterates, that A10 stays of size epsilon to the 1/2, A01 stays of size epsilon to the 1/2, and the two modes A20 and A02 stay of size epsilon. Then we're able to use the Duchon-Robert type argument to establish the next bound for W. So the Duchon-Robert type argument was for solutions without any growing mode. W has no growing modes. The growing modes are A01 and A02. W does not have any growing modes. We've projected W only lives in the space in subspace where all the modes are decaying quite strongly. So that's how we close the induction. We have good initial bounds. We assume we have a bound for a certain iterate, and then given those bounds, we're able to establish the following the bounds on the next iterate using the Lyapunov function for the special modes and using the Duchon-Robert type argument for the next iterates. At several points in that, we have to take epsilon small enough, so smaller than some epsilon star. Then given those uniform bounds, we're able to take the limit as n goes to infinity. So we get this theorem. So there's not much in this theorem other than what I've already said, that the one modes are like epsilon to the 1/2, the two modes are like epsilon, and W, which is everything else, is like epsilon to the 3/2. Then you get a solution of Kuramoto-Sivashinsky for all time. And the L has to satisfy that L1 is just slightly bigger than 2 pi, and L2 is just slightly bigger than 2 pi. And the result is that you get a solution for all time, which is analytic in space for all time. Okay, so a few comments on the theorem. W there was measured in the space B1 row. That probably should be a script B, but W is measured in the space B1 row. That's related to the previously described spaces. It's just slightly different. There were constants in the theorem, M11, M21, M12, M22, and M3. Those constants are all explicit. They're all just in terms of L1 and L2. And epsilon has to be smaller than some epsilon star. We did not track an explicit expression for epsilon star, but it is absolutely possible to do that. And it just depends on L1 and L2 again. So that's the first global existence result for 2D Kuramoto-Sivashinsky that allows a linearly growing mode in both directions. So there are a lot of natural questions about future directions then. Can we do this for bigger domains where we don't require the growing modes to only be slightly growing? Instead of 2 linearly growing modes, can we do this for more growing modes? Could we allow a third, a fourth, a fifth growing mode? Could we do this on domains of any size? So in general, there's a general question that kind of ties up all those questions, which is how can we do better at this idea of tying together a Lyapunov function for finitely many modes with estimates in function spaces for the rest of the modes? Are there better choices of Lyapunov function? Are there better choices of function space? So I'm hoping that this will be a major focus of my research in the next few years, of trying to extend this beyond slightly growing modes and beyond one slightly growing mode in each direction. So I think we can choose better function spaces. I think we can develop more Lyapunov functions, and I think we can get bigger domains. And then you could also try to do other things with this method. You could try to do other things like show stability of traveling waves. And so things like that are also a focus of future research. Okay, that's what I have today. Thanks.